R. Syntax analysis. Syntax analysis forms the second phase of the compiler. The list of tokens produced by the lexical analysis phase forms the input and arranges them in the form of tree structure, called the syntax tree. This reflects the structure of the program. This phase is also called parsing. The syntax tree consists of interior node representing an operation and the child of the node representing arguments. A syntax tree for the token statement is as shown the above example. Operators are considered as root nodes of this syntax tree. In the above case, equals has left and a right node. The left node consists of ID 1, and the right node is again parsed, and the immediate operator is taken as right node. Figure 1.4 syntax tree. The tree has an interior node labeled with ID 3 as its left child, and the integer 60 as its right child. The node ID 3 represents the identifier rate. The node labeled makes it explicit that we must first multiply the value of rate by 60. The node labeled yaon indicates that we must add the result of this multiplication to the value of initial. The root of the tree, labeled equals, indicates that we must store the result of this addition into the location for the identifier position. This ordering of operations is consistent with the usual conventions of arithmetic, which tell us that multiplication has higher precedence than addition, and hence that the multiplication is to be performed before the addition. 3. Semantic analysis. Semantic analysis forms the third phase of the compiler. This phase uses the syntax tree and the information in the symbol table to check the source program for consistency with the language definition. This phase also collects type information and saves it in either the syntax tree or the symbol table for subsequent use during intermediate code generation. Type checking forms an important part of semantic analysis. Here the compiler checks whether each operator has matching operands. For example, many programming language definitions require an array index to be an integer. The compiler must report an error if a floating point number is used to index an array. Coercions, sum-type conversions, may be permitted by the language specifications. If the operator is applied to a floating point number and an integer, the compiler may convert or coerce the integer into a floating point number. Coercion exists in the example quoted position, initial, yaon, rate, 60. Suppose position, initial and rate variables are declared as float. Since the ID 3 is a floating point, then 60 is also converted to floating point. The semantic tree, Fig 1.5, can be seen as follows. The syntax tree is modified to include the conversion, semantic aspects. In the example quoted, 60 is converted to float as into float. Figure 1.5 semantic tree